Okay, for this recording, I decided that I'd go through the Chapter 9 reading guides. I know basically this is a lot of new information for you, and it's really important that you grasp it and understand it so that you can teach it to somebody else. So that we have our section summary, what it's about, learning targets, what you want to be able to do by the time you're done reading the chapter, and it's really important that you actually sit down and read and understand what the book is trying to tell you. A significance test, here's vocabulary concepts. Basically, you'll do a significance test when you want to use a sample statistic to prove a population parameter is wrong. Your null hypothesis, that's abbreviated a capital H with a subscript 0. That's stating what is true. It's a fact given from the population. It's important that when you describe your parameter, you write it in context and that your hypotheses are in terms of your parameter, not your statistic. So, possible examples for your null for right now for one proportion would be P equals some number that we're told, or that mu, the mean of the population, equals some number that we're told. Your alternative hypothesis, which is abbreviated a capital H with a subscript A. This is what we want to disprove about the population. So this can come up with a number of results. We could have less than, greater than, not equal to, and it could be with proportions or means. A one-sided test is when your alternative hypothesis is either less than your number or when your alternative hypothesis is greater than your number. Because you're either going to shade below the lower end or above the higher end. Now remember, this could be the case also with means. You could have your HA being that mu is less than your number, or your HA is that mu is greater than your number. And we would still shade the same as proportions below or above the mean. Once in a while you'll set it up as a less than, and your statistics is actually bigger than the population, so you get this really strange curve where you're shading more than half. Two-sided is when you're shading both ends, because basically when you set up the problem, you're not sure if the sample is going to be less than or greater than. You're only sure that it's not equal to it. So it's not equal to your number. When you calculate it using the test in the calculator, your p-value gets multiplied by 2, which I've already discussed in the notes. So it could be the proportions not equal to the given number, or we could have that the mean, mu, is not equal to the given number. And again, you would shade both ends. Your p-value that you find is the shaded area when you run the test. In context, The p-value is the probability of obtaining the sample results, whatever they are, if the null is true. You can reject the null hypothesis if your p-value is low or smaller than 0.05. And we usually fail to reject our null hypothesis if your p-value is greater than 0.05. 0.05 is just our significance level. That's the standard one that we use. And it's given yet another symbol, alpha, it's a Greek letter, equal to 0.05. Result, your sample is statistically significant if the p-value is less than 0.05. In other words, whenever you reject your null, that means that you have something that's statistically significant. So in the bag of Skittles where people had no green Skittles at all, your results were statistically significant. Next page, there's some things that we talk about more later on, and that's what could go wrong when you do a significance test. You could have a type 1 error, type 2 error. Type 1 error is when you reject the null hypothesis and it was actually true. Your type 2 error is when you failed to reject your null hypothesis and it was actually wrong. Or actually false. The power is the probability of rejecting the null hypothesis, which is our whole goal when we do a test, when it's actually false. And we'll come back to that again after we've gone through tests with both one proportion and one sample mean. Okay, so going through the concept one, the main things behind significance tests, you should read through all that. And here's an actual setup. Suppose you suspect a chute of playing cards is not fair. The chute supposedly contains 10 standard decks shuffled together. That's a lot of cards. A chute is something that you would see like at a casino, and it just is a container that has all the cards, and it's easy to just pull the card right out of it, out of the whole container. So when you're dealing them, it just goes out real quick. So you're interested in knowing whether there are more hearts than usual. So think about that for a sec. We have a deck of cards. There's 4 suits. So with 4 different suits of cards, they should be equally split. So the proportion should be 0.25. To test this, you deal 12 cards at random and calculate the proportion of hearts in your hand. So describe the parameter of interest in the setting. It's the parameter P is the proportion of hearts in the whole population. And in this case, our population are the 12 or 10 decks of cards. So your 10 decks of cards, that's your population. So we have the proportion of hearts in the 10 decks of cards. Now they want us to write the null and alternative hypotheses for the situation. The HO, or the null, is that your proportion is equal to 0.25. And going back up to the problem, we wanted to see if there were more than the 0.25 hearts, that proportion. So we're using that the alternative, your HA, is that the proportion is greater than 0.25. Remember, we're just using the parameter symbols here, not the sample ones. Suppose your deal contains 7 hearts. What's the sample proportion of hearts? Sample proportion, that's your P hat. And it's 7 out of the 12 hearts that you got. So if we calculate 7 divided by 12, we get 0.583. Is it possible to deal 7 hearts out of 12 cards if the chute really does contain standard decks? Is it likely? Why or why not? Well, this is trying to get us to do the test. Obviously, they haven't left us enough room. We haven't gone through the 4-step process yet. So we're just going to calculate our z-score for this. The standard deviation of, well, let's go back to our z-score formula. We know that on our normal curve here, we have 0.25 in the middle, and we're way over here at 0.583. So more than half were hearts. We want to know this little area right over here. What's the probability of getting 58 or more, 58% or more hearts in a hand of 12 cards? So our z-score is going to be your statistic, which is p hat, minus the parameter p, which if you want we can label that as PO because that's what it's in your calculator as, divided by the square root of that same parameter proportion times 1 minus that parameter proportion all over your sample size. So doing this by hand, 0.583 minus 0.25 all over the square root of 0.25 times 0.75 divided by 12, because we were talking about out of 12 cards. We get a z-score of, let me go to calculate this really quick. I'm actually just going to run through the test. Proportion, one prop z test, I went to stat, over to calc, and found one prop z test. Our proportion right now, it should be 0.25. We had 7 hearts out of 12 cards, and I'm guessing that it's more than, and I calculate. Our z-score is 2.66 repeating, and we have a p-value of 0.003, and they also gave you the p hat. So even though it's more than half, and we're only looking for a quarter, it's extreme. It's less than 3 standard deviations away because our z-score is 2.667, but that p-value is still really small. So we're going to use that information, write it down, that our z is 2.667. Now when we used to do this, we would do normal CDF and plug in our z-score, 2.667, and something extremely high. I don't know, 5, 10, 99, whatever you're used to. And we should come out with that p-value of 0.004 and around. Now I just ran through the test and it did the same thing for me. So back when we did the normal CDF, we were actually finding our p-value. So that's saying that this little space right here is only 0.003 of the curve, or 0.3%. of the curve, or excuse me, 0.04. I did round it. Okay, so that was 9-1. Moving on, here's 9-2. Test statistic for proportions. So remember our little saying that was easy peasy? So if we're talking about proportions, we're going to use Z, which implies that we're going to be using our normal model. So we'll be checking the normal model conditions. So your test statistic is just your Z-score, which I wrote the formula down on the last page. It was P hat minus P naught from the population, our parameter, over the square root of that population parameter times 1 minus it, all over n. Significance test, the 4-step process, same as before. We're going to state, plan, do, conclude, mainly because that's how they'll score your test or this problem. And a 1-sample z-test for proportion, well, we kind of ran through one. I'm just going to put how to find it in your calculator. So I'm going to tell you to hit stat, arrow over to calc, and then find one proportion z-test. The p sub 0, that's the population proportion. The x is the number of successes, and n is your sample size. So 1-sample z-test, they run through the state, plan, do, conclude. Notice they're using the p sub 0s as well. That's the actual value. And here's a practice problem here, the 4-step process. So let's read through this problem and do the state, plan, do, conclude. Study of classic authors uncovered a distinguishable speech pattern that differed from author to author. Plato utilized this pattern in 21.4% of the passages in his work. The owner of a rare bookstore claims to have an original Plato work, but you suspect the speech pattern occurs too frequently to be an original Plato work. So what's going on here? You got some guy claiming he has an original piece of Plato's work, which means what? He's hoping to get a whole bunch of money for it, and you're the statistician and you're trying to prove him wrong. So a random sample of passages from the work in question was taken. It was found that 136 of the 439 selected passages followed the speech pattern. So they were looking like they were Plato's. Do these data provide convincing evidence that the work was not written by Plato? Conduct a 1-sample z-test using the 4-step procedure. So going back through the problem, this first value they give you is your population parameter. P, that you could P sub 0, that is 0.214. And then they give you these two values, that's becoming your P hat, 136 out of 439. Where when you're putting in the calculator, x is 136 and n is 439. Now I have to write my parameter in context of the situation. Remember, we want to specify the population. And in this case, in the population, if we go back up to where they describe the random sample, is from the work in question, was taken and it was found. So the whole population is this one piece of work, the original Plato work. So P is the proportion of what they call these passages in the work in question that utilized, I'm just rewriting what they had. Plato's pattern. Now, for my state, I also have to write the HO and the HA. Since we wrote all this information in context, I'm just going to put symbols here, that P is equal to 0.214, and the alternative is that P is less than, because if you look back up, it's saying that you suspect the speech pattern occurs too frequently. Oops, frequently means more than. Too frequently, so more than. So greater than 0.214. Maybe if I went and talked to Miss Grava about this, she would have helped me out with it. I don't know. We'll see. Plan. First step is your sample small enough? Well, they told us we had a random sample of passages. So we have a random sample of 439 passages. And we need at least 10 successes and 10 failures. So again, this is where we use the actual population parameter. We're using our sample size and this 0.214. So this is the first one. The second one is that N times P, which is 439 times 0.214, which is, what's 439 times 0.214? 93.946, which is greater than or equal to 10, and N times 1 minus P, 439 times 1 minus 0.214, I have 345.054, which is also greater than or equal to 10. We've got to write that in context. We have at least 10 passages that follow the speech pattern and 10 that don't. And now we get to say, with conditions met, we can apply the normal model and do a 1 proportion z-test. So the do part, going to go to the calculator and plug in all this information. So I'm hitting stat, going over to test, 1 prop z-test. We were looking at 0.214. We had 136 out of 439, and we wanted more than. If I hit calculate, we end up with a z-score of 4.894. Wow, that's extreme. So since I named it, I'm just copying all this information down. So we have z equals 4.894. Your p-value is, I want to say basically 0. You could write that it's 4.949 times 10 to the negative 7 if you like that better. I'm not writing out all those zeros, it'd be 6 zeros. So say it's basically 0. Your p hat, which was the 136 out of 439, is 0.3098. And if I were to draw this curve, which remember your calculator can do, I'm not going to use the calculator just because it's not going to shade for you. Here's our curve. We have 0.214. It's not going to shade because your value is so extreme. We have one way over here, 0.3098. That this little area, your p-value is basically 0. So, conclusion. Well, I need some paper in order to write this conclusion down. Just a sec. Here we go. Some paper. For the conclusion, I'm going to say with a p-value of 0, which is lower than that standard alpha equal to 0.05, we, or I, however you like to write it, can reject the null, the HO, and we can say we have evidence for the HA. We have evidence that the proportion of passages in the work in question in that population that utilized Plato's pattern, Plato's speech pattern, is greater than .214. If I was also asked to interpret what that confidence means, we would continue on with, or not the confidence, excuse me, explain what the p-value means in context. I would say if the HO or the null hypothesis is true, there is approximately a 0% chance of obtaining .439 passages with 130, what was it, 136 that follow Plato's speech pattern. In the work in question. Okay, so that was concept 1. And then concept 2, they want us to use a confidence interval to draw a conclusion for a two-sided test about a population proportion. So it says a recent study suggested that 77% of teachers have texted while driving. So stop for a sec. That's 77%. That is your proportion of your population. That p sub 0 is 0.77. Random sample of 27 teenage drivers in Atlanta was taken and 15 minutes of texting while driving. So we have 15 out of 27. That's your p hat. It's 15 out of 27. Use a 99% confidence interval to determine whether there's a convincing evidence that the population proportion of teens who text while driving is different than 77%. So this is a different way of looking at it. Now they want us to conduct a confidence interval with 99% in the middle. And remember, back with confidence intervals, the center held our p hat. So this is your p hat. And we're trying to see, does 77% or 0.77 fall in the interval? If it falls in the interval, then we don't have convincing evidence. If it's outside the interval, then we could basically reject the null. You have evidence. Have evidence that for the alternative, p is not equal to 0.77. So that's how we're connecting it right now. So they want us to use a 99% confidence interval, so we don't necessarily have to go through and do our hypotheses. It's not wrong if you put the hypotheses in there. However, I'm double checking right now. I don't believe that you actually have to. Nope, don't need to put the hypotheses in there if we're doing a confidence interval. So we're still going to follow the state. We want to construct a 99% confidence interval to determine the proportion of teens who text while driving. The plan. First one is that random sample, which they told us we had a random sample, so we have a random sample of 27 teen drivers. And now, because we're doing the confidence interval, we can just use our sample info for successes and failures. So we have 15, which is greater than 10, do text while driving. And 27 minus 15 is 12, which is more than 10, don't text while driving. So with conditions met, we can apply the normal model. And construct a one proportion Z interval for confidence level of 99%. Then the do part. Go into your calculator, you put the information in, turn it on, stat, one prop Z int. It's letter A. And we're putting, what was it, 15 out of 27. Confidence level is 99, calculate. The range goes from 0.30923 to 0.80188. So I'm writing all that information down. My p hat, which was from the 15 divided by 27, is 0.556. And my sample size was 27. The confidence interval is 0.309 to 0.802. And then the conclude, we are 99% confident. Uh-oh, I forgot something. I forgot my Z-star. Because that has to tell us how many standard errors. So I look it up on the table. There's that T-table. Down on the very bottom, where infinity is, I go over to 99. It's 2.576. So it's 2.576 standard errors away in either direction. We are 99% confident that the true proportion of teens that text while driving falls between 0.309 and 0.802. So now, bonus, to go back and answer their question. They want us to determine whether there is a convincing evidence that the population proportion is different than 77%. We don't have evidence. That the population proportion, I'm just rewriting the last sentence, of teens who text while driving is different than 0.77, since 0.77 falls between 0.309 and 0.802. If we were to continue on and look at the test for this, one proportion Z test, just so you can see the connection. If I hit stat, go to test, one prop Z test, should still have my information in there. Well, nope, it doesn't. I was looking for 0.77. I do have 15 out of the 27, and we're choosing not equal to. if I calculate, my p-value is 0.008. That's doubled. But what are we comparing our alpha level to? We're comparing the alpha level, if it's 99% on either end, up here, your alpha level is only 0.005. And since 0.77 falls within that interval, we would have failed to reject our null based on this confidence level of 0.99 because the p-value is greater than 0.005. Okay, that wraps up section 9.2. I'm going to go through section 9.3 notes and the reading guide on a different recording.